we oftentimes talk about stress. And stress is not a quantity that you can measure. You have to calculate it. You either calculate it using the response you get from strain gauges, or you calculate it using a finite element analysis, or maybe mathematical equations that you pulled out of a textbook. If we look at stress by definition, here in this case, it's given as the force divided by the cross-sectional area, and it's given as the Greek letter sigma, in this case sigma sub x. So as long as we know the force, and as long as we can measure the cross-sectional area, there's really no reason for us to use a strain gauge if the only thing we're chasing after is the stress. However, oftentimes it's not that simple. Oftentimes you may have an axial load, like in this case, combined with maybe a bending load, or maybe combined with a torsional load. So oftentimes in the real world, these stress scenarios get much more complex and much more difficult to solve. And that's really the power behind using a strain gauge, is that it will allow you to calculate stresses based off of the result you get from the gauge. So if we look at the stress-strain relationship, strain can be measured from the electrical resistance strain gauge, but stress cannot be measured directly. We have to calculate it. And in order to calculate it, we need to understand that relationship between stress and strain for different materials. And all materials are going to be a little bit different, depending on whether they're composites or metals, steel versus aluminum. And this is a real typical graph showing a stress-strain relationship, typically for like a ductile material. If we look at it, you'll notice that we have given the linear elastic region. That's the region at which you can apply loads and release them, and everything goes back to zero. And you'll also notice that we're calculating the slope of that line in the linear elastic region in order to calculate our modulus of elasticity. A few other points that you'll see on the graph, you'll see the proportional limit where no longer it's linear. And then also you'll see a point further up the graph known as the yield point. And that yield point's defined by the 0.2% offset method, which basically means now you've got a 0.2% strain or 2,000 microstrain offset once you release the load. You'll see the plastic region. That's the region at which the material will no longer come back to zero. Now you've got plastic deformation. And then ultimate stress, where you end up going from one piece of material into two. But what I want you to take from this graph is the modulus of elasticity. That's what establishes that relationship between the applied load and the measured strain. The strain is on the horizontal axis. The stress due to the applied load is on the vertical axis. And once you have that relationship, and it's pretty well known for most engineering metals, once you know that relationship, you can use that to calculate stresses from the response you get from the strain gauge. And in order to do that, you use what's known as Hooke's laws. This first one is Hooke's law for a uniaxial stress state. It means a stress in one direction, just like our tension member. So knowing the modulus of elasticity and getting a strain gauge bonded onto the surface, and we measure that strain response, we can calculate the stress, in this case, in the x direction. It's given as the Young's modulus, or modulus of elasticity, times that measured strain. Notice a big assumption. The big assumption is that we've got zero stress in the y direction and zero stress in the x direction, zero stress in the z direction. So we're measuring the strain in the x, calculating the stress, and by default, we're assuming a uniaxial stress state, so we're assuming y and z directions are both zero. And in the real world, that doesn't happen that often. If you're doing material testing with tensile coupons, yes, I would agree with it. But in the real world, oftentimes it's difficult to find a perfect case of a uniaxial stress state. So what do? Well, you end up using another strain gauge. And now you can look at Hooke's laws for a biaxial stress state. If you look closely at the equations, you'll see we've got an equation for sigma sub x and an equation for sigma sub y. And they're going to be a function of the Young's modulus as well as that Poisson ratio we just talked about, along with strain in the x direction and strain in the y direction. So what does that mean to us? Well, what that means is that we've got to install at least two gauges on our structure, one perpendicular to the other, or we put on what's known as a two-element T-rosette, which has two grids that are perpendicular to each other. We take two separate measurements, and from the two separate measurements combined with the material properties, we can calculate the stresses in the X and stress in the Y direction. And the good news for us is that this is as complicated as it gets when solving for a stress field with strain gauges, because strain gauges will measure the in-plane surface strain. The Z direction, they can't measure. That's into the thickness of the material. So we don't have to look at Hooke's laws for a triaxial stress state, only biaxial, because the strain gauge is truly a surface strain measurement. If you're not sure about direction, that's where you typically use a 3-element rosette that's got 3 separate grids on it, and that allows you to solve for principal strains and direction or principal stresses. So keep that in mind. If you're going to use 2 gauges to solve for Hooke's law with a biaxial stress state, you need to know direction. If you're not sure of direction, you really should consider using a 3-element rosette, and we've got a wide variety in different sizes and different constructions that you can choose from. But from the 3-element rosette, you can calculate principal strains and direction, as well as calculate principal stresses and direction as well. I hope that helps you out. If you'd like to find out more about the relationships of strain and stress, take a few minutes and take a look at our website at www.micro-measurements.com, and you'll find a wealth of information related to these topics, as well as many others tied to strain gauges. Thank you and have a great day.